Welcome, curious minds, to the deep dive. Today we're tackling something that honestly sounds like it's straight out of science fiction. It's called time reflection. And for decades, well, it was just theory, pure speculation. But guess what? Scientists at the CUNY Advanced Science Research Center, they've actually confirmed it exists. It's a discovery that really pushes the boundaries of what we thought was possible in physics. This deep dive is inspired by a really fascinating article that just came out in Glass Almanac. And our mission today is simple. Figure out what time reflection is, how on earth they managed to observe it, and what it could mean for, well, everything. Technology, physics. It's mind-bending stuff, so get ready. This one might make your brain do a few flips. Okay, so time reflection. Let's just dive right in. It sounds impossible, right? How do we even start to wrap our heads around something going backward in time? Maybe we should start with normal reflection.
Yeah, absolutely. That's the best way in. Let's talk spatial reflection first. That's the everyday kind. Think about, a ball hitting a wall.
Right? It bounces back.
Exactly. It changes direction in space, but it keeps moving forward in time, doesn't it?
Yeah.
Same with light hitting a mirror or sound echoing off a cliff. Those are spatial reflections. The wave hits something, bounces back spatially. It's like putting a car in reverse. It changes direction on the road, but time still marches on.
Okay, I get that. Direction change in space. But time reflection,
Yeah.
that's a whole different beast, isn't it?
Yeah.
My brain immediately goes to, Marty McFly disappearing or something. How does it work?
It really is a whole different level. It's not about bouncing back in space. It's about the wave's actual progression through time getting altered. Imagine this. You have an electromagnetic wave, like light, or a radio wave traveling through some material.
Okay.
And then suddenly, boom, the properties of that material change instantly and everywhere within it all at once.
It's like flipping a switch.
Exactly like flipping a magical instantaneous switch. And that abrupt change, it forces the wave to, reverse itself in time. Think about hitting rewind on an old VCR.
Yeah.
The picture runs backward, the sound gets all weird and reversed. Everything just unfolds in the opposite order it happened.
Yeah.
That's kind of what happens to the wave. It's not just changing direction. Its entire time, evolution gets inverted. It starts unhappening.
Unhappening. That's a wild way to put it. So the wave's sequence, its history, gets flipped. And I read somewhere this messes with the frequency too. That seems like another layer of weirdness.
Precisely. It's like its history is playing in reverse. And yes, the frequency shift is a key part of it. The source article mentions this too. For example, red light, which has a lower frequency, could shift towards blue light, which has a higher frequency.
Okay.
Or a deep sound could become a high-pitched squeal. It's like that garbled, sped-up sound when you rewind a cassette tape. Remember those?
Oh yeah, definitely. That high-pitched warble.
Exactly like that. All the information's there, but reversed and at a different pitch or frequency. So the wave's time direction, its sequence, its frequency, they all get transformed. And believe it or not, this whole idea, it's actually been kicking around in theoretical physics since the 1970s. Just equations on a page.
Seriously. Since the 70s.
Yeah. But actually seeing it happen, that was the impossible part. Until now.
Okay, that's where it gets really fascinating for me. How do they finally do it? After 50 years, overcoming those technical challenges must have been immense. I'm picturing incredible precision, maybe huge amounts of energy needed.
You're absolutely right. The hurdles were enormous. I mean, think about it. You need to change a material's properties. Not just change them, but change them super fast, practically instantaneously, and uniformly everywhere at once. And you need to do this while an electromagnetic wave, which travels at, the speed of light, is passing through.
Wow. Yeah, the timing alone sounds impossible.
Exactly. The speed, the uniformity, the energy control, it demands incredible precision and sophistication. For decades, scientists just didn't have the tech to pull it off. It required a level of control that seemed, out of reach. It stayed firmly in the realm of theory.
So what was the magic bullet? What did the CUNY ASRC team figure out? How did they build that magical switch you mentioned?
Right. Their approach was really clever. They didn't use some exotic, undiscovered material. They used a specially designed metallic strip.
Okay, a strip of metal.
But not just any strip. It was loaded with these highly responsive electronic switches. Think tiny, incredibly fast switches.
Faster than normal switches, I assume.
Oh, way faster.
Yep.
And these switches were hooked up to capacitors. Capacitors are great at storing electrical energy and then dumping it very, very quickly.
Like little energy reservoirs.
Precisely. Miniature, high-speed reservoirs. Now, here's the genius part. They figured out how to synchronize all these tiny switches. Hundreds, maybe thousands of them.
All flipping at the exact same moment.
in perfect unison. And by doing that, they could almost instantaneously double the electrical impedance of that metallic strip.
Impedance. That's like electrical resistance, right? For waves.
Sort of, yeah. It's the material's opposition to the flow of the electromagnetic wave. So by suddenly doubling that opposition, bam, they created that abrupt change.
The switch.
The switch. But instead of a physical wall in space, it was like throwing up a wall in time for the wave. That sudden change created the perfect conditions they needed. It was an amazing piece of engineering.
So they set up this incredibly fast impedance change.
Mm-hmm.
What happened next? What did the instruments actually show? Did they see a wave rewind?
That's exactly what they saw. During that incredibly brief moment when the impedance doubled, part of the wave traveling through the strip was reflected.
But not spatially.
Not spatially, it was reflected in time. For the first time ever, their instruments picked up a reverse signal, a genuine, time-inverted copy of the wave they sent in. Imagine sending out a little blip of a signal, and what comes back isn't just an echo delayed in time, but that blip playing itself backward.
That's incredible proof.
It was the smoking gun, the first experimental proof. It validated a theoretical idea that had been around for over half a century, moving it from abstract math to something real, something observable in the lab. That's a massive step.
Okay, mind officially blown. So they did it. They reflected time. What now? Beyond the sheer coolness factor for physicists, what does this mean for us, for technology? This feels like it could open up some serious doors.
Oh, absolutely. The implications are potentially revolutionary. Think about wireless communication.
Okay, faster signals.
Faster, maybe more efficient, yes. But the really exciting part, ultra-secure communications.
Oh, so? Because it's reversed.
Exactly. Imagine sending a signal that's already time-inverted. It's essentially scrambled noise to anyone trying to intercept it. It only unscrambles itself back into a coherent message when it interacts with a receiver set up to perform the opposite time reversal.
So only the intended recipient gets the real message.
Precisely. It's like the decryption key is built into the physics of the wave itself. Eavesdropping becomes nearly impossible without knowing the exact parameters of that time reversal process.
That's huge for security. Data privacy, military comms. Wow.
Yeah.
Okay, what else? If we can make things that secure, what about seeing things better?
You're thinking along the right lines. Radar systems are a big one.
Right, radar bounces signals off things.
Yeah, but current radar just listens for the spatial reflection, the echo. Imagine using time reflection. You could potentially send out a pulse and then unreverse the scattered signals that come back. This could filter out noise and interference like never before, giving you incredibly clear pictures. We're talking about detecting stealth objects, tiny drones, maybe seeing things at much greater distances or through fog or clutter with unprecedented accuracy.
So, better eyes in the sky, better navigation for self-driving cars, maybe?
Definitely possible. It could touch air traffic control, autonomous vehicles, defense, and it also leads into advanced imaging in general.
Like medical imaging. Could this let us see inside the body better?
That's a very exciting possibility. Time-reflected waves might penetrate tissues differently, maybe with less distortion. You could potentially get much higher resolution images of things deep inside the body, non-invasively.
Spotting tiny tumors or problems earlier.
Exactly. Or think about industrial uses, inspecting materials for microscopic flaws without having to cut them open. It's a whole new way to probe the world.
Okay, and then there's the M word, metamaterials. This is where we get into the really sci-fi sounding stuff.
Yeah.
Invisibility cloaks. Seriously.
Well, hold on. It's not quite like Harry Potter's cloak yet. But yes, time reflection is deeply connected to the potential of metamaterials. Metamaterials are basically materials engineered with special structures to manipulate waves, light, sound, whatever, in ways that natural materials can't.
Okay.
And if you can control how a wave moves forward and backward in time, that gives you an incredible toolkit for bending waves.
So you could bend light around something.
In theory, yes. You could potentially guide light waves around an object so perfectly that it looks like the light wasn't disturbed, effectively making the object invisible from certain angles.
Wow.
But beyond cloaking, think about ultra-sensitive sensors. You could create a sensor that detects the tiniest change by seeing how it disrupts a perfectly time-reversed signal, or devices that focus energy with pinpoint accuracy for medical treatments, the potential applications in healthcare, defense, telecommunications. They're really broad and could fundamentally change things.
It's not just gadgets, though, is it? Does proving time reflection exists change how we think about, well, time itself and space?
Yeah.
the fundamental rules?
That's a really deep question, and yes, it absolutely does. For physicists, this is incredibly profound. It challenges our everyday intuition about the arrow of time, the idea that time only flows one way.
Right, forward.
Showing that, at least for waves under specific conditions, time can be reflected, suggests a deeper symmetry between time and space than we usually acknowledge. It might force us to rethink some fundamental concepts. It could have knock-on effects in areas like thermodynamics, the study of energy, heat, and entropy, or quantum mechanics.
How so? Quantum mechanics is already pretty weird.
Well, maybe this gives us a new tool or perspective to explore things like quantum entanglement or how information behaves in extreme situations like black holes. We don't know yet, but opening this door, it forces physicists to ask new questions, to probe the limits of our current understanding of physical laws. It's a window into potentially deeper physics.
Wow. Okay, what a journey we've been on, from a 1970s theory to an actual lab demonstration with potentially world-changing implications. The confirmation of time reflection really feels like a landmark moment. It's hard not to get excited about where this leads.
Absolutely. It's a fantastic reminder that sometimes the most abstract, theoretical ideas, the ones that seem like pure mental exercises for decades, can suddenly unlock incredible breakthroughs. They didn't just do a cool experiment, they validated something fundamental and opened up pathways we couldn't access before. Mastering time reflection. Yeah, we might genuinely be on the edge of a new scientific and technological era. The possibilities are just starting to unfold.
It really makes you wonder. As we step onto this new frontier, here's something for you, our curious listener, to chew on. Beyond communications and radar and metamaterials, what other secrets of the universe might we uncover using time reflection? How could manipulating time, even just for waves, fundamentally alter how we perceive reality itself? Keep thinking about that one. We'll catch you on the next deep dive.